Good day, I'm Norman Walberger. We're looking at the deep structure of the rational numbers. And last time I introduced the Stern-Brokow tree going back to the mid-19th century. This is it right here, and it's an interesting way of exhibiting the rational numbers that are positive, that are strictly positive, the things that we usually call fractions. So in this tree, which actually keeps on going down and down, there are further and further rows below, every fraction appears exactly once, and it does so in reduced form. So 7 over 5 appears exactly in this spot in the infinite binary tree. And going from any one spot to the two below it involves taking what we call the mediant operation. So to get this one from this one, we actually look at this fraction as well as the next one to the left above it, and then take the mediant of these two, meaning we add the numerators and we add the denominators. Similarly, to get this one from 3/2, we go to the right above it to the next one in the table that's to the right and take the mediant of these two, getting 5 over 3. So that is the Stern-Brokow tree. Today we're going to have a look at a variant of it where we replace the fractions with matrices. That's going to be in some sense simpler, even though the matrices are a little bit more complicated than the fractions, because they allow us to answer the question of how do you go from an entry to the two below it if you don't know anything above that entry. We're also at the end of the lecture going to talk about geometrical manifestation of the Stern-Brokow tree, a planar representation that leads to a rather interesting idea of certain very narrow triangles, which we're going to call wedges. Gives us some more insight into this deep structure of the rational numbers. So this is the question that we're interested in. How do we determine the elements directly below any given entry of the Stern-Brokow tree? We can call the two elements below a given entry, maybe its children. And the answer is we're going to look at the matrix form of the Stern-Brokow tree. And a good reference for all this material is the lovely textbook Concrete Mathematics by Graham, Knuth, and Patashnik. A lovely textbook on combinatorics and computer science related mathematics. Donald Knuth, also the creator of the mathematical typesetting language TeX. So we're going to need just a little bit of information about matrices. So we're going to look at 2x2 matrices, and we're only going to look at matrices with integer values, so-called integral matrices. And what a matrix is an expression of this form. Some round brackets, and then A, B, C, D. For integers, A, B, C, D. So it's 4 integers arranged in a nice little 2x2 array. These matrices are very important in linear algebra, and if you want to find more about them, you can have a look in my linear algebra YouTube series, Wild Lin Alg. And here are the operations for addition and multiplication of two matrices. Addition is component-wise. So to find the top left corner entry of the sum, we just look at these two top left-hand corner entries and add them. The product of the matrices is a bit more complicated. To find this top left-hand corner of the product, we don't just take A1 times A2. We take rather the first row of the left matrix and the first column of the second matrix, and we multiply them in a suitable way. And what that means is we multiply A1 times A2, but we also add B1 times C2. That's that entry there. This entry here is A1 B2 plus B1 D2, the first row times the second column. This one is the second row times the first column, so C1 A2 plus D1 C2, and this is the second row times the second column. We're only really going to be using a little bit of matrix multiplication, not very much in this lecture. So here is the matrix form of the Stern-Brokow tree. It starts at the very top with this matrix, which is a rather special 2 by 2 matrix. It's usually called the identity matrix. 1, 0, 0, 1. It has the property that when you multiply any matrix by that one, you get the matrix you started with. And it doesn't matter whether you multiply it on the left or the right. Here are some more matrices. These are also rather important matrices, as we'll see. And then the table kind of continues. And the pattern is actually surprisingly simple. So to go from this entry here to the 2 below it, what you do is the following. You take the matrix here and you look at its columns, the first column and the second column. And to get this entry here, what we do is we add the second column to the first. So add the 1, 1 to the 2, 1 to get 3, 2. And leave the second column where it is. And to move right, what we do is something similar. We take the first column and add it to the second column, giving us 3, 2, and leaving the first column where it is. So another example, starting with here, 2, 3, 1, 2. First column 2, 1, second column 3, 2. To move left, we add the second column to the first column, giving us 5, 3, and 3, 2. To move right, we add the first column to the second column, giving us 5, 3 on this side, and 2, 1 on the other side. So these outside 2 columns of the 2 children are necessarily the same. They're just the sum of the top 2 entries and the sum of the bottom 2 entries. Matrix form of the Stern-Brokow tree. And here is the official rule for creating this matrix form. We start with the identity matrix up at the top. And below any matrix A, B, C, D, we have the 2 branches going to this one and to this one. This is the one where we add the second column to the first column. This is the one where we add the first column to the second column. Now it's very convenient to define these 2 matrices, L and R. So they're a lot like the identity matrix, except that L has a 1 in this left sort of corner, and R has a 1 up in the right corner. The reason why it's interesting is because then this branching operation can be described very efficiently using matrix multiplication, either by L or by R on the right. So if you take this matrix here and you multiply it on the right by the matrix L, then you will get this matrix. And when you take this matrix and multiply it on the right by the matrix R, then you will get this one. And it does make a difference whether you multiply on the left or on the right, because matrix multiplication is not commutative. The order does matter. So this is a very efficient way of describing how we create this matrix form of the Stern-Brokow tree, starting with the single matrix, the identity, up at the top. Just go left and right, corresponding to the branches left and right. Okay, but how do we recover the original Stern-Brokow tree from this matrix form? What we do is we associate to the matrix A, B, C, D the fraction A plus B over C plus D. When we do that, we can replace each of the matrices with a fraction, and then we get exactly the Stern-Brokow tree that we started with. So for example, instead of the identity matrix, if we add the top and the bottom, we get 1 over 1. Instead of R, we would get 2 over 1. Instead of left or L, we get 1 over 2. And this matrix would correspond to 1 over 3, this one to 2 over 3, this one to 3 over 2, this one to 3 over 1, and so on. Now it's interesting to make the observation that since going left or right corresponds to multiplying by the matrix L or the matrix R respectively, it means that any element that we can generate in the tree can be described in terms of a successive number of matrix multiplications. For example, to get this matrix here, we start with this matrix, multiply by R, which is just R, and then multiply by r again to give what we might call r squared. If we wanted to go down here, well, we would multiply at this stage this r by L on the right to get RL. This would be L, and then this would be LR, and this would be L squared. And then we realize that now what this gives us is a way of associating to a fraction, like 3/2, a sequence of R's and L's, or maybe L's and R's, depending which way it starts. This is a very interesting and somewhat surprising benefit that just sort of drops into our laps by looking at this Stern-Brokow tree. That we now have a way of associating fractions to essentially binary sequences. So every matrix in the Stern-Brokow tree is either the identity matrix up at the top or a product of L's and R's, because they're obtained by either going left and right, starting from the identity matrix. That means that every rational number r bigger than 0, in other words every fraction, can be associated to a unique, finite, binary sequence of L's and R's, with the special case of r equals 1 associated to the empty sequence, which corresponds to the matrix I. So for example, the sequence LLLRL corresponds to the matrix that you get by starting with the I and going left, 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 right, left. And that turns out to be this matrix here. And in terms of matrix multiplication, it's just the matrix L times the matrix L times the matrix L times the matrix R times the matrix L. It's a product of these 5 matrices in the algebra of matrices, 2 by 2 matrices. And then we saw that this matrix corresponds to the fraction 3/11. So this fraction 3/11 corresponds to this sequence, and the sequence corresponds to 3/11. Another example, sort of pulled out of the hat, RRLLRL, which would correspond in the tree to going right, and then going left, and then right, and then left. That's the matrix 12, 7, 5, 3. You might like to check that. And then that corresponds to the matrix 19/8. The most efficient way of checking this is not by doing the matrix multiplication, but just remembering that the operations corresponding to either adding the second row to the first row, that's an L operation, or adding the first row to the second row, that's the R operation. So if you start with the identity matrix and you do the RR operation, and then the LL operation, and then R and then L, you're going to get this matrix, corresponding to 19/8. So we're using the word finite sequence here in a rather loose way. We haven't completely clarified what this means. In fact, it's actually an important task to think about what exactly we mean by a sequence. It's a very crucial question in this whole analysis story. So next video we are going to have a look at that, but for now we're just going to adopt a little bit of an informal approach. We're just talking about sequences of L's and R's after all in this case, so it's just a bunch of symbols. Each of them is either L or R. So I've explained how to go from a sequence of L's and R's to a rational number R. A natural question is, how do you go backwards? Given the rational number R, how do you recover what the sequence of L's and R's is that corresponds to it? Well, that's a fascinating question that opens up a big chapter of number theory. Rather elementary number theory, but still pretty interesting, historically interesting number theory called the theory of continued fractions, which goes back to Euclid and was much studied in the 17th and 18th centuries. So we're going to talk a lot more about continued fractions a little bit later on in the series. You can think of this page here as just a little introduction to the ideas, just enough so that you could actually make some computations yourself. So how would we go from 3 over 11 to this sequence LLLRL that we used in the last page? So here's the idea. Maybe it's a bit like magic if you've seen it only for the first time. 3 over 11 is less than 1. We would like to have something bigger than 1, so we're going to take 1 over its reciprocal. So 3 over 11 is the same as 1 over 11 over 3. And then we replace 11 over 3 with 3 plus 2/3, because that's a mixed fraction, the same as 3 plus 2 over 3. And now we look at this 2 over 3 and sort of play the same game with that. Replace it with 1 over its reciprocal, 3 over 2, and then rewrite the 3 over 2 as 1 plus a half. And then finally look at the 1 over 2, and that 2 at the bottom can be written as 1 plus 1. And so here we have a rather complicated looking fraction. 1 over, this is all in the denominator, 3 plus, and then this thing here is one entity, 1 over 1 plus 1 over 1 plus 1. And from this we can extract some L's and R's by looking down these numbers here and seeing we have 3 corresponding to 3 L's, and then an R, 1, and then 1 L. How about 19 over 8? Well, this is already bigger than 1, so we can just write it as a mixed fraction, 2 plus 3/8, which we'll write as 2 plus 1 over 8 over 3. This 8 over 3 can now be rewritten as 2 plus 2/3. The 2/3 rewritten as 1 over 3 over 2, just like we did over here. And similarly, we'll just get 1 over 1 plus a half, and then 1 over 1 plus 1 over 1 plus 1. So now we have a sort of a sequence of numbers here, 2, 2, 1, and 1. And sure enough, there's 2 R's, and then 2 L's, and then 1 R, and then 1 L. So we're associating to a fraction, one of these sort of continued fractions with lots of reciprocals going down. And then reading off these numbers here, we can interpret them in terms of some sequence of R's and L's, or L's and R's. So you might like to play around, have a look at that matrix form for the Stern-Brokow tree, make some calculations, associate rational numbers to matrices, to strings of R's and L's, and work with it. Do some examples, go lower down in the tree so you get some more interesting examples, and see sort of how that correspondence works. You can happily spend a few days doing that. It's a lot of fun. In linear algebra, the theory of matrices is closely associated with the older theory of determinants. And in the 2x2 case, the theory of determinants is pretty simple, although for higher matrices it's more complicated. The determinant of the 2x2 matrix A, B, C, D is this number, AD minus BC. So this times this minus this times this. We've seen AD minus BC before quite a lot of times when we're talking about fractions, when we also talked about adjacent fractions. You may remember that two fractions A over B and C over D were adjacent precisely when this expression was either plus or minus 1. So the main theorem about determinants is this one, which actually holds for any square matrices A and B, not just 2x2 ones. But in the 2x2 case, you could actually check it yourself. The statement is that the determinant of the product of two matrices is the product of the determinant of A times the determinant of B. So you can check this by actually working with two general matrices A and B and working out the left-hand and the right-hand sides. The significance of the determinant, you should think of it perhaps in terms of an area. If we associate to the matrix the vectors AB, say along the first row, and the vector CD along the second row, then we can think about the determinant as representing the area of this parallelogram that we form. It's actually a signed area because if you interchange the order of the two vectors, then the area changes sign. And we don't have to work with the rows, we can also work with the columns. So we could look at the two vectors AC and BD, and the determinant would also still represent the area of the the parallelogram formed by them. The identity matrix has determinant 1 because 1 times 1 minus 0 times 0 is 1. The matrix L has determinant 1, as does the matrix R. Now every matrix in the Stern-Brokow tree was either the identity matrix up at the top, or it can be written as a product of L's and R's. And so if we use this theorem repeatedly, any product of L's and R's is going to have total determinant 1 because each of the matrices L and R have determinant 1. So for example, if you multiply L times R, this rule tells us that the determinant of L times R is the determinant of L times the determinant of R, which will then be 1 times 1, or 1. So that's a property that all the matrices in the Stern-Brokow tree have, and you can check that. They all have determinant equal to 1. So I now want to introduce a third version of the Stern-Brokow tree. This is a geometrical realization of the tree in the plane. More specifically in the positive upper quadrant of the plane. So here we have the x-axis, the y-axis labeled 0, 1, 2, 3, 0, 1, 2, 3, and so on. We have the various integral lines and the various points on the plane represented by ordered pairs A and B. And we're interested in a particular situation here, thinking of the origin as a special point, perhaps the sun. So imagine that you have the sun right here. The sun is beaming out rays of light. And we're interested in which of these integral points in this quadrant is visible from the sun. That is, there's room for a ray of light to get from the sun to the point. So this point here, 3, 4, is visible. So if I draw that line there, even though it gets close to some other integral points, it actually misses them. So some photon could go straight from the sun to this point here. But the point 4, 4 does not have that property because the ray from the sun to 4, 4 would first bump into 1, 1. And so this point 4, 4 is in the shadow of 1, 1. In fact, that's all of these points here. That's why they don't have dots on them. So what I've shown you here, the points that actually have dots, they are the visible points. Okay? And that really amounts to that the coordinates A and B are relatively prime, that they have no common factors. What we're going to do now is we're going to think about this plane as being another way of thinking about rational numbers. Okay, so because we could take one of these visible points, A, B, which has the property that A and B are relatively prime, and associate to it the fraction A over B. So to this point here, which has coordinates 5, 2, we can associate the rational number 5 over 2. To this point here, which is the point 7, 5, we can associate the rational number 7 over 5, and so on. That has an interesting advantage. Okay? The interesting advantage is that now the fraction 1 over 0, which is not really a fraction, it's not really a rational number, it's still represented by a visible point here because it corresponds to the pair 1, 0. There's the pair 1, 0 there. That's that point there, which is just as legitimate a point as any other one. We've talked about this representation of rational numbers actually earlier in this series, and I remind you that we can connect that with our usual notion of rational numbers in the following way, by thinking of this line here, the line where y equals 1, as being the number line, not this one here, this one here. So to any point, say 7, 5, that one there, I can draw the line from it to the origin, and I can draw that line and see where it meets our number line. Okay, it would meet it right about there. And that would be a point on the number line, which you would usually call the point 7/5. We've just scaled the y-axis coordinate down so that it's equal to 1. So this is a way of sort of visually blowing up the rational numbers so that they're not just sitting on this line, but now they've been kind of expanded into the plane where we can see them a little bit more clearly. They separate themselves. Okay, so once we've done that, well, then we can draw the Stern-Brokow tree in this situation. Now it's sort of starting from here and going outwards. So this is the apex. This is 1, 1, or 1/1. This is the number 2/1, the number 1/2. And we can draw a bond between 2 points precisely when there's a bond in the Stern-Brokow tree between the 2 fractions. So for example, there's a bond between 2/3 and 3/5, and that's why there's a line between the point 2,3 and the point 3,5. And every point here ends up having 2 children that sort of in that direction, and each one is the child of a single one other one. So this is a third planar or geometrical form of the Stern-Brokow tree, which I think is somewhat novel and reveals yet more interesting structure of the rational numbers. It's interesting because it has geometrical content now. We can actually talk about the geometry of this picture, not just the combinatorial structure. It's not just a binary tree anymore, it's something with geometrical content. So we're introducing some quite new ideas here, and probably later in the series we'll come back to them and explore them at a little bit more depth and leisure. But right now I'm on my way to cutting down real numbers. That's high on the agenda, so this is just a temporary little diversion. Okay, we're looking now at the Stern-Brokow tree in planar form, and I want to connect the matrix form of the Stern-Brokow tree to this geometrical form. We gain new insights by doing that. So let's make the following sort of definitions. Consider the matrix A, C, B, D. And I purposely changed the order of the 4 numbers from what I usually do. So usually I write A, B, C, D. Now there's an A, B, C, D. All right, so suppose that's a matrix in the Stern-Brokow tree somewhere. I can associate to that a triangle, which is 3 points. One of the points is AB, the first column, written as a point. The other point is the second column, CD, written as a point. And the third is the sum A plus C over B plus D. This third one corresponds to the fraction which we usually associate with this matrix in the Stern-Brokow tree. So for example, if we look at the matrix 2, 5, 1, 3, then associated to that are 3 points. One of them is the point 2, 1. The other one is the point 5, 3. And the other one is the point 7, 4. So 7, 4 is right here. 7, 4, right up there. And 2, 1 is here. And 5, 3 is here. So these are 3 visible points. These two happen to be connected by a bond in the Stern-Brokow tree, telling us that 7, 4 is actually the child of 5, 3, the direct child of 5, 3. We might call 5, 3 the mother of 7, 4, and we might call 2, 1 the father of 7, 4, the father being older or higher up in the tree. The mother has exactly 2 children. The father has many children. But it's not exactly a sexist situation because all 3 roles are shared by any one point. So except for the identity matrix, all the other points are both fathers, mothers, and children sort of in different roles. You can think about those comments, maybe a bit curious. All right, so what's going on here? What we've done now is, to this 0.74, it corresponds to the fraction 7 over 4, and this is the corresponding matrix for it. So the fraction 7 over 4 appearing in the Stern-Brokow tree is associated to the matrix, this one here, associated to the same position in the matrix form of the Stern-Brokow tree. And now to that point, or to that fraction, we now associate a triangle. This actual triangle in the plane. This kind of triangle is called a wedge. So for every matrix in the Stern-Brokow tree, we get a wedge. And it has an interesting property. It has area equals a half. This is the minimal area that a triangle with integral points in the plane can have. So this is in general sort of a long, skinny triangle. This one may look long and skinny, but for bigger matrices, the triangles are much longer and much skinnier. They become very hard to visualize. So every fraction r has an associated wedge w sub r. So in this case, if r is equal to 7 over 4, then this triangle is the triangle w sub 7 over 4. And, well, so we get lots of wedges. And what's sort of interesting is that we end up getting a tiling of this quadrant. The wedges fit together like a jigsaw puzzle to fill out pretty well all of the quadrant. Not quite all of the quadrant, because the non-visible points are not included. It's the visible quadrant that's filled out. So for example, shadows of points are not covered. And this triangle here is also a bit of an exception. So together with this red triangle here, the wedges w sub r, where r is a fraction, tile the visible positive quadrant. So here are some other examples of wedges. This wedge here, for example, is associated to the point 1/2. This wedge here associated with point 2 over 1. This wedge here associated with point 3 over 1. This one here associated to 2/3. This one here associated to 2/5. And I haven't drawn more, but if I drew more, you see that they fill up the entire visible positive quadrant. And there's some interesting properties of these things, which I might talk a little bit more about later on in this course. It's a lovely diagram, but it's maybe not so easy for human beings to appreciate, because the triangles become very thin, very long and skinny very quickly. So when you look at it, you see all these really thin little wedges, and it's not like a usual tiling kind of picture. But nevertheless, it's quite rich mathematically and reveals yet again the deep structure of the rational numbers. That's what's being reflected in here. Next time, we're going to start investigating sequences of rational numbers, moving towards understanding Cauchy sequences, limits, and the various problems associated with the standard approach to real numbers. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.